assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
This question says a sample of pure NO2 is heated to 337 degrees Celsius, at which temperature it partially dissociates according to this equation. At equilibrium, the density of the gas mixture is 0.52 grams per liter here, and the pressure is 0.75 atmospheres. It asks us to calculate the Kc, or the equilibrium constant with respect to concentration, which is shown here, what that would be. So this is a tough question because it doesn't give us a whole lot, but these values at equilibrium that are for the whole mixture of gases, so we need to figure out what's going on with each gas. Let's set up our ice table. And to do this and make it simple, we're going to assign an arbitrary number to what the starting material is. This number isn't important. It's all relative at the end, but I'm just going to say 1. We have 1 mole of NO2 to start this reaction, and we have none here. Like I said, you could make this 100. It would change the calculations, but the end result would be the same. I'm just going to do it 1 to keep it simple. And so let's put the change. This would be minus 2x. This would be plus 2x. And this would be plus x. Then we can write out what the equilibrium amount would be. 1 minus 2x, 2x, and x. So these are the equations we have for the equilibrium number of moles in the reaction. So let's do the total number of moles, because we'll need this for the ideal gas law later. So I'm writing NT for the total number of moles. That's just going to be the sum of these 3 parts here. So 1 minus 2x plus 2x plus x. And this comes out to 1 plus x. So this is an equation for the total number of moles of gas at equilibrium. Okay, a couple more equations we need. The density, is the sign rho here, is equal to the mass over the volume. And the symbol for molar mass, let's use capital M, is equal to the mass over the number of moles. 2 equations we'll need in just a moment. And we're eventually going to plug these into PV equals nRT. And we can rearrange these so that we can get moles, number of moles, in terms of other values that we might know. So if we rearrange this, we can get N equals mass over molar mass, and we can rearrange density to be mass equals density times volume. And we can plug this mass into this so that we can get N equals density times volume over molar mass. And we can plug this into this equation so that we can get PV equals density times volume over molar mass times RT. All of this was just to get a new equation where we can have a molar mass term, which we'll solve for in just a moment. We have volume on both sides, these will cancel out. We have the pressure, it's 0.75. We have the density, it's 0.52. We have the ideal gas constant, it's 0.08206. We have temperature in Kelvin, 610. And then we can solve for molar mass. Molar mass is going to be equal to 34.71 grams per mole. Now we have a molar mass of the gas mixture, which of course isn't helpful. We need to find the individual gases. So we can express this term, molar mass, which we just said equals 34.71. We can say that is equal to the mole fraction of each gas times its own molar mass. So if you remember, there's these types of problems where you can, if you were given the natural abundance of an isotope and you knew the mass of that isotope, you can find the average atomic mass of the element. Very similar here. We can do the mole fraction of each gas times its molar mass, give us this number. So that would be 1 minus 2x. That's the number of moles of NO2, and the total number of moles we just found was 1 plus x. And this will be times the molar mass of NO2 plus number of moles of NO, which is 2x, over the total number of moles, 1 plus x times the molar mass of NO plus number of moles of O2, x over 1 plus x times the molar mass of O2. We know we can look these up, the molar mass of each of these terms, and then we can simply simplify this and solve for x. I'm not going to plug each of those in, but for NO2 it's about 46, for NO it's about 30, and for O2 it's about 32. So if you plug those numbers in here, you solve for x, you would get x equals 0.3254. Great. And so this is what we can plug back into here to find the number of moles of each compound. And I'm going to real quickly rewrite this on a new page because we're running out of space here. Rewrite this equation. 2 gas, equilibrium with 2NO gas and O2 gas. I'm just going to copy, going back here, I'm just going to copy this line here, the equilibrium equations. So we have 1 minus 2x, we have 2x, and we have x. And if we plug in, we found that x equals 0.3254. We can figure out what each of these are. This would be 0.3492. This would be 0.6508. And this would be 0.3254. Again, this is moles of each of these gases. So again, from that long, drawn out derivation here where I tried to get a value for x here based on the molar mass, which I could calculate from all of these pieces, and this kind of weighted average of the molar masses of each of the gases, I was able to find the number of moles of each gas at equilibrium. But this question is asking for the equilibrium constant, Kc, which is in terms of concentration. So we need to divide these moles by the volume of the container to get the terms we need to solve for Kc. But we don't have a volume. But we do have PV equals nRT. Again, I'm not going to plug in each of the parts, but we do have all of these. We have P. P is 0.75 atmospheres. We're looking for volume. We have the number of moles. From previously, you remember number of moles total equals 1 plus x. We now have x. So this is equal 1.3254. So that's the number of moles here. We know the ideal gas constant, 0.08206, and we know the temperature in Kelvin is 610. So we can solve for volume, and volume equals 88.48 liters. Now with this, we can figure out the concentration of each of these gases. If you divide these three numbers by 88.48, you get new numbers, which are about 0.003947. Kind of writing out a semi-rounded form of each of these. You should keep these in your calculator when you're doing this straight through. Moles per liter. Here we'd have 0.00736. Moles per liter. And 0.003678. Write this down here, that's also moles per liter. Okay, now we have concentrations of each of the gases. We can plug them into the equation for the equilibrium constant. This is the concentration of NO squared, concentration of O2 divided by concentration NO2 squared. And when you solve this, if you plug in these concentrations, which I'm going to do real quick, we have you get, sorry for the delay, if you plug each of these values in here, you get a final answer of about 1.27 times 10 to the negative second. That's the equilibrium constant with respect to concentration, Kc, for this reaction. And one more time, just going to review what we did, because there was a lot here. Set up an ice table using an arbitrary starting number of moles for the reactant gas. Then, by rearranging using equations for density and for molar mass, we were able to calculate the molar mass, the average molar mass of the mixture of gases at equilibrium. And from that, we were able to solve for our x term using the molar masses of the gases in this reaction. We found x to be 0.3254. We plugged that back in here, and we found the number of moles of each of the gases. We then calculated the volume of the container using this equation, all the terms we now have, found the concentration of each of those gases, plugged those in for Kc, and we were able to solve for the equilibrium constant.